and spend a few minutes here and listening to an expert on the subject about how to be successful. We're indeed grateful to welcome Dr. Richard Zare, who is the Marguerite Blake Wilbur Professor in Natural Sciences at Stanford University. Dr. Zare, we're truly pleased to have you here with us at BYU. The Reed M. Izatt and James J. Christensen Lectureship is held annually and acknowledges outstanding contributions to chemistry and chemical engineering. Reed Izatt and James Christensen initiated a joint program at BYU many years ago that focused on chemical thermodynamics and chemical separations. This was a remarkably productive collaboration that lasted a number of years. It was responsible for graduating over 60 master's and doctoral students under their tutelage. These scientists also authored or co-authors books, book chapters, and peer-reviewed articles totaling over 860 between them. Professor Christensen passed away suddenly in 1987. But we are honored to have Professor Reed Izatt here and his wife, Janet. Reed and Janet, would you stand just so we could acknowledge you, please? We also want to acknowledge the many donors who have contributed to this lectureship so that we can enjoy this type of activity here at BYU. Before we have our invocation, may I remind everyone to please turn your cell phones off. It's a lot like the theater.
That's me.
Additionally, immediately following Dr. Zare's lecture, we will have a reception in the garden court. So please come and join us there and take a few moments to get acquainted with Dr. Zare. Our invocation today will be offered by Professor Adam Woolley, who is an associate chair in the Department of Chemistry and Biochemistry. After the prayer, Dr. Milton Lee, who is the Tracy Hall Distinguished Professor of Chemistry and Biochemistry, will introduce our guest, Dr. Zare. Adam?
Our Father in heaven, we are grateful to be gathered here this day to hear this lecture. We're grateful for Professor Zare for his taking the time to come and visit Brigham Young University and impart some of the wisdom and experience that he has accumulated over the years, and that he will be able to, we ask thee to bless him to be able to teach us as he has planned, to be able to And we ask thee to help us to open our minds that we may learn, that we may gain insights, and that we may be uplifted as he teaches us this day. We thank thee for this university, for the grateful facilities that we have, and for the dedicated faculty and staff who work here at this university, and also for the students who are the reason that we're here. We thank thee, Father in heaven, for all of our many blessings, and we ask thy blessing to be upon this meeting this day, and we ask this in the name of Jesus Christ. Amen.
For those of you who are in the back, there are chairs up here. Just come up and fill in. Maybe some of you can move in because we have people waiting on the outside. If you wouldn't mind doing that, that would facilitate so everyone could enjoy this lecture. Those in the back, just come on up. There are 4 or 5 seats up here. There are some over on the wing side over here, and 2 or 3 up here in the front. Well, Professor Zare is a graduate of Harvard University, where he received a BA degree in chemistry and physics in 1961 and a PhD in chemical physics 3 years later. In 1965, he became an assistant professor at the Massachusetts Institute of Technology, but soon moved on to the University of Colorado, where he held joint appointments in the departments of chemistry and physics and astrophysics. He then went to Columbia University for 8 years before moving to in 1977 to Stanford University, where he has been there ever since. He served as chair of the chemistry department at Stanford from 2004 just till last year, and he says he's enjoying not being chair right now. He's also been active in public service at the highest levels, for example, serving as chair of the National Science Board, which is the policy-setting body of the National Science Foundation. Professor Zare is an enthusiastic and dedicated teacher, you'll notice that today, who has taught freshman chemistry almost every year he's been at Stanford. His teaching efforts and mentoring have been recognized by many awards, including the Presidential Award for Excellence in Science, Mathematics, and Engineering Mentoring, the George C. Pimentel Award in Chemical Education, and Stanford's highest award for undergraduate teaching. Dr. Zare is also renowned for his research in lasers applied to chemical reactions and analysis, and he will speak tomorrow in the chemistry department on this subject, on the subject of short-lived intermediates at 4 o'clock in a seminar there. Among his numerous awards, he is the recipient of the National Medal of Science, the Welch Award in Chemistry, the Wolf Prize in Chemistry, the Priestley Medal, and the Frontiers of Knowledge Award in the Basic Sciences, and the King Faisal International Prize in Science, which he just received last year. The latter two awards are international awards that recognize world-class research that pushes back the frontiers of the known world. I was interested to learn that the King Faisal Prize is given each year in a ceremony in Riyadh, Saudi Arabia, by the King of Saudi Arabia, and consists of three things. One, a certificate describing the accomplishments of the awardee, handwritten in Diwanee calligraphy. Number two, a 24-carat, 200-gram gold medal uniquely cast for the awardee. And three, a cash prize of approximately $200,000 US dollars. This must have been quite an occasion, yeah? Dr. Zare has trained over 100 PhDs, authored and co-authored over 800 scientific publications, and co-authored more than 50 patents. He holds 10 honorary degrees at universities around the world in countries as far away as the People's Republic of China. Dr. Zare and his wife of 48 years have 3 daughters. Please join me in welcoming Professor Richard Zare to Brigham Young University to speak on a subject about which he's obviously an authority, how to be successful. Dr. Zare, it's a pleasure to have you here.
Thank you, Professor Lee. I think it does take a certain amount of bravery combined with foolishness to decide you're going to talk about a subtitle about how to be successful. But to be serious, I hope when I finish you'll have a sense of what I mean by this and how everyone really can, I think, find a way to be successful. Let's begin this topic here, how to be successful. If anybody wants a copy of this talk, just email me, okay? And I'll send you the PowerPoint so you understand what I'm saying. Let's see. Yeah, let's talk about the road to success and how is this road paved. And from my experience, it's very much about problem solving. All types of problems in life. Some get solved, some don't, actually. Okay, all types of problems. And of course, you face them when you go to college, for sure. High school, but particularly college. And so seldom does anyone really talk about how to solve a problem. Let's, though, get involved in this. No, I mean, seriously, they don't. At least that's my experience. Okay? The question is, can we teach problem solving? And here's a famous overview written by this man, Johnstone. I think he's in Scotland somewhere. And he has this picture of about events, observations, and instructions going through a perception filter, interacting, rearranging, comparing, storage, and preparation in our mind, storing, retrieving, sometimes branched, sometimes as separate fragments, long-term memory, feedback. It's a lovely picture. Folks, I've never solved a single problem with this picture. I don't know about you. So I'm sorry, it may be great for those in a certain field, but it doesn't help me solve problems. So let's continue. How do you find something out? Okay? Well, one place to look is at cartoons. And I think I like this cartoon a lot, and you can learn from it. It's one of my favorite cartoons. It shows two little boys and a dog. And this little boy is pointing towards this dog, and he says, I taught Stripe how to whistle. And of course, Stripe only has spots, but never mind. Those are cartoons, right? That's the first panel of the cartoon. And the second panel of the cartoon, this other boy is holding his ear up to the dog's mouth. And he says, I don't hear him whistling. And then the final panel of the cartoon, I said I taught him. I didn't say he learned it. As teachers of chemistry, I've been there. But this is a really profound question, whether we can teach how to solve problems. To what extent? Maybe we can only foster something here as opposed to teach it. But we're going to talk about it. I want to at length anyways. Let's begin. Let's begin with the background. Students usually act like the solution is more important than the method of finding the solution. As you heard, I teach beginning chemistry. All the time, students are running up to me and they say, what's the answer to problem 3A? And I ask, how are you trying to solve it? And they say, never mind, just tell me the answer. And I'd say, if I change the problem, I'll get a different answer. The answer's unimportant. What are you doing? Etc. But often, there's confusion here. It's not the answer. It's the process that's really important. I think agreed? Okay. Teachers seldom talk about how to find solutions to problems. And when they do, students usually see a clean, even elegant solution having little in common with the fuzzy thinking that they experience when they try to solve problems by themselves. Yeah. Here, let me show you, right? We go all these steps and it's done, and then you go away and you say, well, I guess you could do it that way, but then what did he do? I've been there. So next thing I did is, again, how do you learn about things? One of my favorite ways to find out information is Google. So I Googled problem solving. One of the first things I came up with is problem solving tips, T-I-P-S. This seemed all very clever. What's the T? Thought process. Think about the problem, decide what you're being asked to find. That makes sense. Information. Write down or highlight the key words, numbers, and facts that need to be considered. Good. Plan. Decide on a mathematical operation or strategy and set up how you will work out the problem. Sounds good, but how do you do it? Ask solution. Solve the problem by performing the strategy you choose. Don't forget to make sure your answer makes sense by estimating and checking in your head. Well, okay, that's all good, but that's not really helping me too much here. Some, but not too much. It is getting me focused. The first two really make sense to me. More tips. So I looked further into Google, and what I could find were some further hints about what to do. And to me, these make great sense. Decompose problem into smaller problems. That's a good strategy. Sometimes you can get overwhelmed when you look at the whole problem, like lots of things. Like, what are we going to do with the nation's budget? Overwhelming, right? But we talk about smaller pieces, we have ideas what to do, okay? If the problem is too hard, think of a similar problem that you can solve. That helps you get started, what to do. Draw diagrams, make tables, list facts. I might add to this, play. Be willing to play, to fool around with the problem. Examine possible limiting cases. Try things to extremes to find out, what does it matter? They talk about the temperature and the pressure in some problem. What if the pressure is nothing? What if the pressure is 1,000 atmospheres? What if the temperature is really hot or really cold? Does it really matter about temperature or pressure? To what extent? Find out what's going on. Make guesses and approach solution by iteration. That is really the way most computers solve lots of problems. Seriously, is by iteration. It's a way very few humans can admit that that's how they actually get somewhere, is to try something, see if they're getting close, and readjust what they try. But it's really valuable. Don't forget that. Okay? So what do the experts say? Let's look and see. Textbook solutions to problems provide no indication of the false starts, dead ends, illogical attempts, and wrong solutions that characterize the efforts of students when they work in problem solving. Me too, okay? But there are some beautiful articles. There's one by Heron, Research in Chemical Education, Results and Directions, okay? But the one I like best of all is by this man, George Bodner, who I guess has just recently taken retirement. He's at Purdue University in the chemistry department, and he has written a paper called Problem Solving, the difference between what we do and what we tell students to do. That's worth reading. So what does Bodner tell us? An experienced teacher uses a linear, forward-chaining together a logical sequence of steps and progressing smoothly from the initial information to the answer. I've seen it. But a routine exercise for a teacher using a simple algorithm becomes a challenging, novel problem for a student who encounters this task for the first time. It doesn't work that way. So what do you do? Bodner found that an anarchistic model describes what successful problem solvers do when they work on novel problems in chemistry. I might add, novel problems in any field. I don't think this is limited to chemistry today. I think it pertains to chemistry, some of what I'm telling you, but I think it's bigger than chemistry, what we're talking about. What do? You try something, and then you try something else if the first try fails. That's really what you do, okay? You try to learn from failure. This is a secret. Failure can be a guide to success, but people don't look at it that way. Some people don't want to admit they ever failed, okay? This is nonsense. If you think I'm successful, let me confess right away to you, I have failed all the time and continue to fail at things. Incidentally, there's some seats right over here, and I get nervous when people stand, so please come in. It's okay to leave anytime you want also. But come on in, okay? Well, we'll continue. Watching an instructor wade effortlessly through the task is not usually a sufficient teaching tactic. The student must stumble on his or her own personal algorithm for completing a task. Okay? So the take-home message. This process of trial and error may appear disorganized or even irrational to the teacher, so that intervening to show the student the correct way of obtaining the answer is tempting. People come with a problem. They come to you, how do you solve it? The teacher then produces a solution. That's not that useful, okay? Really not. While intervention may make the teacher feel good, oh yeah, it does not necessarily help the student. I want to go backwards. Hope this. Now how do I go backwards with this? Let's give this a try. There. So what do you really do if you're trying to be a teacher? What you do is when somebody comes to you with a problem and you have an idea how to solve it, is you ask the student another question. Have you thought about this? Have you thought about that? What do you think? Is there any connection between this and that? And that is the way you help people really solve a problem, not by showing them how to solve the problem. Yes, it takes a longer time, but they go away knowing how to solve the problem. And moreover, having then the spirit of problem solving, because that's what you want. Once you solve one problem, you can solve the next, and it builds, it grows on itself that way. I've seen this so. One form of problems is crossword puzzles, right? And how do you get good at crossword puzzles? By doing more crossword puzzles. And why do you do crossword puzzles? How do you get into it? Well, you have some success. If you had no success, you'd give up. Hate crossword puzzles. You start to have some success and you build on it. That's what goes on. Many games are situations in life are very much like that. So here's one problem-solving strategy which I found quite fascinating. It's called working backwards. And again, people don't talk about this much. But there was one man who did, and his name was George Polya, and he was a math professor at Stanford who wrote a book, How to Solve It, that's now out of print in Princeton University Press. It's a great book if you can find it. And what did he say? Polya thought that a problem is best addressed by examining what is it that the question asks us to find, called the objective, and by working backwards to the information given in the question. So you start with the objective and you think how that relates back to what information is given in the question. Okay? So working backwards. Let's examine this. We are interested in creating a problem-solving pathway that travels from the objective to the givens. Now, this same strategy actually works in chemistry, in synthetic chemistry. It's called retrosynthesis, for which Professor E.J. Corey got the Nobel Prize. And let me explain that to you for anybody who doesn't know. You start with a complicated, say, natural product, something that nature's made that's really complicated. And instead of saying, well, here are all the simple compounds that you can start to make this natural product, what do I choose? You say, what must have been the last step that brought two things together to make this natural product? Then you ask, well, if it's that, how could you then make those pieces the same way? This then leads back to, okay, now I need to get myself some simple starting materials to make it work. It's very powerful. And you'll see this in other contexts. Here's one. I bet all of you have sometime as kids worked about solving mazes, walking through a maze to get out. How do you make a difficult maze? I can tell you how. When you first walk in, you don't know whether to go up, down, or sideways, right? You're confronted with 3 different paths. So as a kid, quickly, I learned that the quick way to solve a maze was you start here, and you work back. With pencil, you trace it out. Works quite easily that way. Okay. Now, of course, you could say, well, I could reverse the maze, but people don't. And so there's a very simple first strategy for solving maze-type problems. I'm going to give you a different type of problem, let you puzzle about it, and see if you like it. This is a game, and this is the game. You travel by car, starting in Provo, Utah, we know where that is, through all the 48 states in the U.S. You can only enter and leave a state once, staying within the U.S. Okay? No travels to Canada or Mexico. We stay in the U.S. We're going to visit all 48 states. My question to you is, what is the second to last state you will visit? And it is New Hampshire. That's correct. But let's see, how do you get that? How do you get that? First of all, you need, unless you're one of these people who walks around with photographic memory, you need a map of the U.S. I brought one. Let's locate where we are, okay? Now, here we can go down, we can go up, we can go sideways. All these are possible. For there to be an answer to this problem, because let's go back to what Polly is telling us, there must be a last state which is unique. That means one state which is only bordering one other state. And I heard it. Did Janet say it? I'm not sure. Yes? No? Okay. It's Maine. It's Maine. Maine is the only state which only touches one other state. And so the answer is New Hampshire, which is what you said. And the path? Many. Okay? But you get a sense again of the power of this type of reasoning to solving some problems. It's very interesting. Then there's more games of this sort. I think next, let's go back with some more experts. A brilliant person, alas, no longer with us. A person who's famous for both economics and psychology and should be famous for computer science. But he was in the days before there was a computer science. This man, Herbert Simon, developed something at Carnegie Institute of Technology before it became Carnegie Mellon or something, called IT language, internal translation. IT language was the forerunner of something called Fortran, which came before C, C++, and so forth. This was a brilliant guy. He was worrying about how could machines solve problems? And here's what he came up with. He says, what you do is you define a problem space, all possible configurations. And then you're in a problem state, some particular configuration like you start with, like in Provo, Utah, right? And the key to solving a problem is to choose the right operators, legal processes that apply to change the configuration. And problem solving is a search process. Each action takes us from one part of the problem space to another, is his idea. And the problem solver compares the present situation with a goal, detects a difference between them, and then searches memory for actions that are likely to reduce the difference. So you ask yourself, what is the difference between current state and end state? What can I do to reduce this difference? And you make a list of means for reducing this difference. That was his idea. And indeed, this is exactly the way computers play chess. I'm an avid chess player. I didn't say I was good. I said I'm an avid chess player. I really enjoy playing chess, but okay. And so I'm interested in this. Today, computers, I think, can beat everybody at chess. They've gotten to that stage. There's still some human activities like Go game, which so far people are better than computers. But so far in chess, I think the advantages are now with computers. And what do? They examine each position, make all possible moves, all possible legal moves, and keep computing what goes on, and they go further deeply into this, right? Great. Very interesting. But you know, I don't play chess that way, and I don't know any human who does either. You don't have the patience to make all possible moves, etc., and you don't do that. No way. So next, as I say, the beat goes on. A Canadian by the name of Mary Gick wrote an interesting paper called A Distinction Between Schema-Driven and Search-Based Problem-Solving Strategies. And what is she talking about? She says, here's the problem. You construct a representation, and you see whether or not you can recognize a pattern. If you recognize a scheme, is a scheme activated, you jump ahead. And if you don't see a pattern, then you use the search for solution, looking again to try to recognize a problem. That's very much her idea. And indeed, that's how I do lots of things in thinking about things. There's a part of me is really looking to find patterns in things that I've seen before, and then I can apply what I've done before. That's why I told you in crossword puzzles, once you do a bunch of them, you get better at it. The same is true of every form of problem solving. Let's go back to another type of problem. Playing the piano, right? Reading a book, How to Play the Piano, will not teach you how to play the piano. How do you learn to play the piano? You got to play it. The same thing's true about problem solving. You got to solve problems. Try solving problems. Okay. So this is, I just summarized Gick's model. Let's move on. Here's another interesting problem I liked, I came across. What is the next member of this coded series? Here's a code. And it's not at all obvious to begin with what is the next member. At least it wasn't obvious to me. And perhaps some people, it's a big audience, somebody will know, but you do, okay? Let's go on. Here's the key. Look for symmetry. And I'm serious. Anytime you can apply something involving symmetry to a problem, you always reduce its complexity. You simplify the problem for yourself. So look for symmetry. Is there a symmetry in these symbols? Well, yes, there is. Look at this is reflected on this. This is reflected on this, right? And now block them off. See this? See this? See this? That's 4, that's 5, that's 6, that's 7. Oh, now you know the answer. Problem solved. And you even know the rest of the series if you want them, right? And that's through applications of symmetry. That's neat when that can happen. And powerful. All the time. Believe me, standard fare for anybody in the physical sciences. Look for symmetry. Let's go on. Here's still another approach to problem solving. become obsessed with your problem. Now, seriously, you won't become obsessed with your problem unless you really think it's important. This is going to tell you something further about what you want to do. If it's not important to you, no way to become obsessed with it. When you become obsessed with your problem, then I can talk to somebody, and while we're having some type of idle conversation, or go to some, silly lecture like this one right here, and somebody will say something, and click, I'll see how to solve my problem. It's true. But you have to be with your problem. And it happens that way. Okay? Here's another strategy. Dream about it. I've actually solved problems by dreaming about it. Now, I don't know about your dreams, but my dreams are incoherent. They make no sense. They're not logical. But the dream actually clears your mind and allows you to go in a new path, often that you don't otherwise do. And so there's been famous examples of many problems solved by dreaming about it. I had the pleasure, as you heard, of winning something called the Wolf Prize in chemistry. And I was sitting in a taxi going about 100 miles an hour between Jerusalem and Tel Aviv with two Russian mathematicians who also had won the Wolf Prize in mathematics. They did it in some field called topology, and I know like nothing about topology. And I'm at the moment a bit terrified because I think I'm going to die on this road with these distinguished other people. And I have to make some conversation. So I turned to them and I said to them, "You've solved some problems for which you're famous." I said, "How did you solve the problem?" Because I'm very interested in problem solving. And I wish I could do a Russian accent. There are other people who can better than me. And they said, in deep voice, "We mathematicians, we have tricks." "Oh," I said, "did you use a trick to solve your problem?" Some more discussion in Russian followed back. "All good mathematicians know the same tricks." "No, we didn't use a trick." So I asked, "So how did you solve the problem?" Some more discussion in Russian followed by, "We don't know." But I'm telling you, while they don't know, and people give them all types of credit, see, the world's celebrating some of these problems, and problems that come in dreams and all the rest, it doesn't matter. They're celebrating the solution to the problem, not the person. There is an aptitude, an attitude that really allows you to solve problems. And some people have it, and moreover, you can learn it. This is what I'm talking about, fostering something here. You really can pick this up, and I'm hoping you'll get some sense of this from this lecture. Let's move on. Here's another strategy. This is called thinking outside the box. And here's my favorite example of this. The objective is to draw 4 connected straight lines that pass through every circle. This is a 3x3 array of circles, and I'm being asked to draw 4 connected means they touch each other, okay? Connected straight lines, straight, you understand? Okay, that pass through every circle. And the way I first started to work this problem was something like this. Okay, here we go. First line, second line, third line, fourth line. Oh dear, 5 lines. And then because of symmetry, I could start going in other directions, and I always ended up with 5 lines. I couldn't solve the problem. Okay, but there is a solution. And just for fun, those who know the solution, there's a bunch. Most of the audience, excellent, excellent. So I show you, not everybody though. So here's the solution. You really go outside the box. In this case, the periphery, right? Here's the first line, the second line, the third line, the fourth line. Problem solved. Beautiful, right? That's really outside the box. Now, you have to get into the spirit of outside the box. And so the next things I'm telling you about, I've made up. Here we go. Draw 3 connected straight lines that pass through every circle in this 3x3 array of circles. And first reaction of some people is you can't do that because parallel lines, don't meet. So, I mean, you can't do this, right? But think about this some more, and I'll show you a solution. here's a solution. 1 line, 2 lines, 3 lines. Nothing said it had to go through the center of each circle. I just said it had to go through the circles, right? Okay, now that we're beginning to get in the spirit that I want you to get into for this, because this is the type of spirit that really leads to breakthroughs of problems. Let's go to the next problem. Draw 1 straight line that passes through every circle in this 3 by 3 array of circles. Now, I can hear some solutions. I want to call on somebody. Please. Yes, a fat brush, right? 1 fat brush will do it. Okay, that's solution number 1. Now, what if I told you, I put a constraint. The width of the line must be less than the diameter of a circle. What would you do? What would you do? And I'll show you. Okay? You put your thing on a cylinder. And 1 straight line will go through all the circles. Now, I thought I was being clever, right? And then somebody showed me that you could actually do it with a line of almost no length, which just shocked me. And what he did is he sent it to me. He took the 3 by 3 array of circles and he folded them so all the circles were overlapping each other, and he put a pin right through the center. Now, you may think this is very silly, but I think it's not. I think it's profound. I think it really tries to get us to see that there are ways to look at things that break through, otherwise, assumptions we make, which limit our ability to solve problems. So this is really thinking outside the box in a big way, way, way outside the box. Okay, we'll go on. Here's a problem which I was sent that really had me going for about an hour. Very sad problem for me. This is graph paper. Hope you recognize it. And you see this triangle over here? It's 1, 2, 3, 4, 5, 6, 7, 8 by 1, 2, 3. Well, this one here is 1, 2, 3, 4, 5, 6, 7, 8 by 1, 2, 3. This piece is this piece. 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 What's going on? Why are you bothered by there's a missing square? I was deeply bothered. I was so bothered that I took this and I cut them out and superimposed them on each other. It's true. They really are the same. Then my youngest daughter, the least mathematical in the family, came by and she says, "Daddy, what are you doing?" And I said, "I don't understand how these 2 triangles can be made of the same pieces and one has a missing square." And she looked at me and she said, "Daddy, they aren't triangles." And that was brilliant. And they're not. I'll show you what I mean. Some of you might remember the definition of what's called a tangent. It's the side opposite over the side, side opposite this angle over the side next to it. Well, the tangent of here is 1, 2 by 1, 2, 3, 4, 5. 2 over 5 is not the same as 3 over 8, is it? And if you look very carefully, neither one of these is a triangle. Wow. Quite amazing. Once again, if you want a copy of these overheads, just email me and you'll get them. You can see for yourself. Okay? And this is really the problem. I bring this to you. This is what happens when you make a wrong assumption about a problem. You can spend forever and never solve the problem. Be careful about what assumptions you're making, often hidden. No one said to me, they said, "Are you bothered by this?" Well, I shouldn't have been bothered by it at all. Okay? Quite interesting, I thought. Let's take another example. This next one I think I show you is pathological. It's quite amazing. It's hard to believe. You see this square A? You see this square B? You think A and B have the same color? I don't, right? Which one you think's darker? Which one you think's lighter? Seems pretty clear to me, right? Are the colors of the squares A and B the same? So let's just take this thing and let's just drop black things on this. Okay, here's the first one. Here's the second one. Here's the third one. And look, there's no way that they're the same. Fourth, there's no way they're the same. So I'd say no, right? Well, let's continue. First one, second one, third one, fourth one, fifth one. Oh, we're getting into sixth one. First one, second one, third one, fourth one, fifth one, sixth one, seventh one. They're the same. That's called an optical illusion. That's the problem, is the way our minds wired up. We're so taken by this object here and the idea of shadows and what we perceive that we make them different. It's amazing. Okay, may none of your problems have those aspects to them. Right? Okay, now we're going to turn to a coin problem next. And I want to give you the sense of this, because we're in the spirit now of playing with this. Here are a bunch of coins, and our goal is to transform this object of 6 coins into these 6. And I need to explain, a move consists of sliding one coin to a new position where the moved coin must touch 2 other coins, and no other coins are allowed to move. You get to slide them. So let's now blank off this projector and try to turn this one on. And fine. Oh, good, good. And now, hope you see these are lined up this way. Okay, let me ask Professor Reed Izatt to come on stage, if you would. And we want to look at this problem together. Okay. First, you can look at this too. What I'd like you to do is to make a legal move, to actually take a coin, and we're going to go towards making it into a hexagon, a benzene ring. Okay, so here's a coin, and look, that's great. It's almost there. If I could just now move this one here, I'd be done, right? But only one coin can move, and this one's locked into position. So hard to know what to do next. Do we do something like this? Where are we going? We go here, and if we go back here, we're back where we started. Right? Just rotates around. So thanks. Reed, unless you see a solution, I'll leave it to me, right? I have given this problem to many, many people. My experience is that people do not solve this problem at all quickly. You can try this on your friends, if you'd like. It's not at all easy to see. But there's a way to solve this if you think back to what I was telling you. Let's look. What we're trying to do is, see if we can make this. We're trying to make this object, right? That's our hexagon. If we start with the hexagon, what must have been the next move to make this? Probably something like this by symmetry. They'll all look like this, right? Now, this one moves here. This one moves here. 3 moves. Let me do it in reverse order, now that we've seen what to do. This one comes here. This one goes here. This one goes here. Problem solved. Again, the power of thinking backwards, working the problem backwards. The power of retrosynthesis. Quite interesting. Good. I'm going to now turn this off. Okay. And we've seen that. And I think that's a fascinating problem in its way. Try it on your friends who haven't come to this lecture. And that's what I'm showing you. Here, I have another friend in Italy. This is a person who teaches beginning chemistry. His name is Liberato Cardellini. And both of us share a fascination with problem solving. And Cardellini sent me the following problem to solve. And I thought I would relate it to you. I did have a laser pointer. And it ended up over here. Okay. What is it? Two Italian men meet who have not seen each other in many years. While catching up on each other's news, the first discovers the second has married and has 3 daughters. The first asks their ages. The second answers, the product of their ages is 36, and their sum is equal to that house number over there, pointing to the number under the porch of the house. The first one replies, I can barely see the number, but if what I see is correct, then this information is insufficient to know their ages. Oh yes, replies the first, I forgot to tell you that my youngest daughter still has blue eyes. Hopefully you know that people are born with blue eyes. Okay. How to solve this problem? Okay. He said I could solve it, and so I must be able to solve it. And it's because he said I can do it, and he's a friend, I can't let him down, right? So I decided to set it up mathematically. I don't know how you'd go about this, but this is how I went about it. I said, let x, y, and z be the 3 ages, right? The product, x times y times z, is 36. The sum equals a house number over there somewhere. And x has blue eyes. It's going to be the youngest. It's very hard to solve this problem mathematically. So I got frustrated. And since he told me this has a solution, I decided I can solve it. I'm going to take the number 36, and I'm going to factor it every way possible into 3 things that make 36. Here we are. 1 times 1 times 36, 1 times 2 times 18, 1 times 3 times 12, 1 times 4 times 9, 1 times 6 times 6, 2 times 2 times 9, 2 times 3 times 6, 3 times 3 times 4. And then I summed them up. And what did I notice? Look, these 2 sum to the same thing. That's the comment about that's insufficient information, followed by blue eyes. There's a solution. Problem solved. Once again, it may sound silly. How did the problem really get solved? Because I wouldn't give up and felt there had to be a solution, and we were going to continue to work at it. Incidentally, a lot of research gets done this way. You have to persevere. You have to believe you can do it. Do something about it, right? This is so. Okay. Here's another problem I made up. This one's more chemistry. After all, there should be some chemistry here, right? An aqueous solution of hydrochloric acid, HCl, is electrolyzed, causing the release of hydrogen gas at one electrode and chlorine gas at the other electrode. We'll use DC to do this. This electrolytic cell is placed in a closed, sealed room having one entrance. Wires lead to the electrodes, and there are 3 switches outside the room, but only one switch is connected to the electrolysis cell. Okay? Here we go. Here are the 3 switches. They're all in the off position to start with. You're allowed to play with the switches all you want, turning them on and off before entering the room. You get to enter the room once. Which switch? You have to know which switch runs the electrolysis apparatus. What to do. Here's chlorine on one, hydrogen on the other. Here's the electrolysis cell. We don't care about details like 1 molar HCl. Okay, sealed room, one closed door. You get to open it. Wall, can't see. Get to go through the door once. What to do? If you think about it, there are 3 possibilities, so I got to eliminate 2 of them. So I better have 2 observations that'll help me eliminate this. And so here is, as I say, how do you determine which of the 3 switches is connected to the electrolysis cell? Okay? I could stop here, and you think you have a solution. Okay? I thought I would, if I might just tell you a possible solution. This is a solution I was thinking of. You go to switch number 1. You turn switch number 1 on, say, for like 10 minutes. Then you turn switch number 1 off. Then you flip on switch number 2. At this point, you enter the room. If you see no bubbles, but you smell chlorine, it's switch number 1. If you see it bubbling away, but don't smell anything, it's switch number 2. If neither of those statements are true, it's got to be switch number 3. Problem solved. Maybe that's the type of solution you had. You did. Thank you. Yes. And this is, again, the type of logic. But I'm really trying to get you to see something here. This is not all done just by mathematics at all, or it is done by putting together experience and reasoning of different sorts. But it's all a matter of playing with it. And so let's now come. I'm sorry, I don't know how long I've been going at this. Hope I haven't worn you out. Belief that a problem can be solved. I want to tell you about two stories, if I might. One of them I don't believe is true. Oops, hit the wrong. Let's go back. Ice cream story, if I might. What's the ice cream story? It's a story I got when I was at the National Science Foundation that someone sent in to us about buying a car, a Pontiac. There was a time, once upon a time in Detroit, where they made a car called the Pontiac. This person bought a Pontiac from his dealer, and then he took the Pontiac back to the dealer, the General Motors dealer, and he said, "You've sold me a lemon. This Pontiac's no good." It's a brand new car. What do you mean it's no good? He says, "Well, every night after dinner, we all hold hands, and then we vote what flavor ice cream. There's a store which only provides ice cream, and we go to this store, and every time I go with your new car and I ask for vanilla, your car stalls. If I ask for any other flavor, it's fine, but it doesn't work on vanilla, and I want my money back." Pontiac dealer said, "This story is nonsense. I'm not giving you your money back. You're just crazy." So then he wrote a letter to the president of the Pontiac division. Same thing about the dealership's no good, nor is your car. Well, okay, so the president sent over some automotive engineer to go look at this thing, comes in, and they have dinner. He's invited for dinner. The man's overjoyed. Someone's paying attention to his problem. And afterwards, he says, "Let's now decide what flavor of ice cream." And the engineer says, "I didn't come here to decide what flavor of ice cream. We're going to go get vanilla." They get in the car. They go to this place that only sells ice cream. For those who know, Friendly's is the name of the store type of thing. But anyways, and comes back with vanilla. Car won't start. Work at it. Get it started. Drive it home. Drop it off. It says, "Turn around. Go back. I want you to go get, fudge ripple." Goes in. Comes back with fudge ripple. Car starts right away. Goes back. Says, "Turn around. We're going to get vanilla again." Goes back. Goes get vanilla. Car won't start again. He says, "It's real." He says, "Of course it's real. I want my money back." Engineer says, "Tomorrow I'm coming." and we're going to look into this problem more deeply because I'm convinced this problem has some solution. Incidentally, this sounds like a lot what goes on in my lab, one crazy thing after another. Okay? And you have to believe that there's logic behind this or some nature going on, and this engineer did. And now, being really a good scientist, a good engineer, he is measuring everything. He's looking at the air temperature, the air humidity. He opens the hood of the car, brand new. Okay? He looks, is there gas? There's gas in the car. Okay? He looks at the air pressure and the tires. Everything's fine. He goes there. And now he goes in with a man to get the ice cream. And he finds out that vanilla is so popular that they pre-package their vanilla. You just walk up, you pick up the package of vanilla, and you pay, and you're on your way back out. But if you want any other flavor, they hand pack it. And God forbid they should give you too much ice cream, right? So they put much in, and it takes them out, and they put more back in. Then they pack it some more, and it all takes time. And once he realizes it's a function of the time that the car has been shut off, the solution's obvious. It's something called vapor lock. If you have a rich fuel mixture and you haven't let the car cool down enough, you can't start it up again. You won't make the spark to make it go, to ignite the gas mixture. And so problem solved by a very simple carburetor adjustment. That's the ice cream story, which I don't believe ever happened, but it's a wonderful story. The next story I tell you, I know happened. It happened to a friend of mine. It was his thesis. And his advisor had a device at that time at the Georgia Institute of Technology, which had 2,048 channels, and they were collecting some type of data on some gas phase ion molecule reaction that was rare. And they would have to run for days to collect their data. They gave that little signal. Okay? But they noticed that they would get noise spikes that would knock out channels. And the longer they ran, the more noise spikes they got, and pretty soon they couldn't do the experiment because they were overwhelmed with noise. What to do? The professor said, this device, this 2048 channel device, it's really supposed to be good, but it's not working at all. I know that there's somebody in the physics department who has one. Go swap with this person in the physics department. You give him ours, and we'll take theirs, and just to try it out. They do that. Now the device which was not working in the professor's lab is working over in physics, and the device that came from physics is not working. Same thing, getting noise. Ah, he says, see, it's not the device. It's clearly the electricity. These people at Georgia Institute of Technology, you know, they don't pay enough money to maintain the electricity in the building correctly. There must be noise spikes that are coming in. So he calls up the buildings and grounds. There's always a name for these things. I don't know what it's called here. It's a maintenance type thing. He says, no good. Electricity. He said, what do you mean? Our electricity is perfectly good. He said, no good. Prove it, he says. So they then bring in a recorder, a strip chart recorder that records the electricity. And the electricity is absolutely solid, straight line all the time. But they learn something from this because they watch the time. And they get most of the noise early in the morning, around lunchtime, and around leaving time. And it really works well at night. They don't know why. Something's happening. They can't figure it out, and they're stuck. It's a true story. It's not necessarily a pleasant one. One of the members of the research group got sick, actually got diarrhea. And it turned out that the men's room was immediately next to the lab. And the discovery was made that it was possible to literally flush away the data. That when you flushed the toilet, you got a noise spike. Suddenly, things started to make sense. Turns out they have what's called a diffusion pump. That's oil that you heat up and evaporate and condense, and they have a water cooler on it to protect things. And should the water fail, you see, you have to be able to shut off the diffusion pump. It's an interlock, it's what it's called. And a relay's there. But the relay's gotten old, and it now, when it senses the water pressure goes down, it thinks it's being shut off, and it fires. Okay? And the problem is solved, and this person got his thesis. But took a while. Well, real story. And what's the point of all this? Again, importance of confidence, the importance of belief that you can really solve a problem and to go for it and to care about it. So if I might, I'd like to now reach a conclusion to all this. And problem-solving skills can be developed. It's a wondrous place. We advance our understanding of it by posing questions and seeking answers. Celebrate the joy of aha, a thrilling moment of discovery, and so forth. And the real challenge, are the givens sufficient to solve the problem? You saw when they weren't, false assumptions. Are the givens as stated? Is the objective worth attaining? Are we asking the right question? That really is the most important thing, okay? Can you do all types of things with your life? Pick something that matters, okay? And then if I might, in the spirit of a late night TV show, I'd like to give you a top 10 list of elements of a successful career, okay? And this is stuff I want to leave you with on this. So if I might, number 10, take responsibility for managing your own career. No one else will. Avoid the trap of getting caught up in the expectations of others, particularly your parents. Polonius said it, to thine own self be true, okay? This is so, okay? 9, plan your career. As the great American philosopher Yogi Berra said, if you don't know where you're going, you might end up someplace else. But life is more a stochastic process than is first imagined. One crazy thing after another keeps happening to you. Consequently, long-term planning is less useful than it might seem. When opportunity knocks, open the door. Always make plans, but be flexible and be willing to reassess your plans. Have a plan, but be willing to change your plan. Talk to people who quote unquote are successful. Did they plan what they did when they were young? Most of the time, no way. Okay? No way. It's a matter of stumbling around the right way. 8, practice persistence. You may or may not need a PhD, but you do need dogged persistence in solving problems. Good things never come easily. 7, seriously, don't grow up. I never have. Peter Pan was right. A childlike, I didn't say childish, a childlike sense of wonder allows great creativity and invites discovery. You were born with a sense of wonder. Don't lose it because it's not regarded as adult behavior. Serendipity can be made to happen, and like lightning, once it strikes, it can be made to strike again and again. Once you're in that right frame of mind, you can do it. Okay? Become a happy, contented schizophrenic, believing and not believing at the same time. I mean this. I mean this very much. If you believe too easily, and I've met such people, then you will delude yourself. You really will fool yourself. Most quote-unquote scientific things that go wrong is because people fooled themselves. Okay? If you are too critical, you will never try the outlandish. Haven't you met people who are really great critics of writing, and they're such good critics of writing that they themselves can't write because they're so good at critic at writing? You can't do that, okay? Become your own worst critic, but simultaneously dare to try something different. Put forward an idea and immediately turn around and try to think what's wrong with it. It's really an important skill. Okay? 5, embark on a program of continuous self-improvement. Now it's easy. You're in college, most of you, right? Remember that a dull axe requires great strength to chop wood. Be wise and sharpen the blade. Keep on learning. You can learn not just in classes. Okay? 4, seek challenges. A little-known secret is that it takes about as much effort to solve a hard problem as an easy one. Don't wait for your ship to come in. Row out to meet it. Okay? Seek challenges. Pick the right problems. 3, go to people you trust and respect for career advice. Recruit mentors and make friends. I cannot emphasize enough the importance of the value of critical friends, someone who will not simply tell you what you want to hear, but will speak the plain, unvarnished truth, even if it hurts. These are people I look forward. I tell them an idea. They say, wow, or they say, what? And you want that. You really want people who can react that way. Okay? Critical friends are priceless. Of course, when you ask this of others, you must be willing to offer the same quality of friendship to others, right? But it's important to find such people. And 2, keep your life in balance. I think for me, this has been one of the hardest things to do. No job should serve as a substitute for your family or for a rich personal life. Make your work something you love. Life is short and a career is even shorter. If you don't love your job, you better think about leaving it for some other job that you do love. Be aware that no perfect job exists. They don't. There's nothing. There's nothing that works. People come to me all the time. Oh, I want to do experiments. And I say, you realize you're going to spend a lot of your time doing plumbing, looking for short circuits. Okay? Okay. Oh, no, I'm going to do theory. You realize you're going to spend a lot of your time looking for errors in computer programs or looking at integrals that diverge. Okay. Be aware that no perfect job exists. Every task has its drudgery and its frustrations. I like to cook. That means I also need to wash the dishes. Okay? They go together. Okay? No situation is free of politics. What is important is to be able to pass through the negative so that you can dwell happily in the land of the positive. Blessed are those who achieve equanimity in this age of angst, stress, and false gods. And now, the most important, in my opinion, number one. Okay? Have a dream and do something that you love. Build sandcastles in the sky. Their foundations will follow. Select something that you love, something that you value. Study it. Live it. Work at it. Work harder at it than you've ever worked before. Immerse yourself totally in it. In that immersion, you'll find happiness and contentment in a life truly well lived. That's my recipe for success. Thank you all.
Dr. Zare, you provided a fascinating piece of guidance to us and some interesting problems for us to go off and think about more. Thank you, and thank each of you for coming. Remember, there is a reception now out in the garden court. Please come and take a moment to visit with our guest. Thank you. Oh, one final announcement. For those of